Okay. Yeah, that's mine. Going to full screen. So, who am I? Mikael Rosbacke, software developer like C, C++, that kind of stuff. State machines, going a little bit old school here. We have seen them before, so one more try to actually be usable. So, we've all done the switch case. You have a hierarchy that you can set up, a state chart if you want to be strict on names. So, how do you do this in C++ in a fairly decent way, more or less? So, I've written a small helper, I wouldn't call it a library, a C file, a CPP file, and a header file. The scope for this is more or less make it easy to write these state machines. There's no code generation tool. I want entry actions and exit actions, support for that one. Hierarchical, so when you switch state from one place to another and you pass down and pass up, all that should be automatic. So that's really good to have, I think. Microcontrollers, I like them. I want to be able to use this there. So no heap allocation of the construction. And intended for this sort of application logic, not just hopping around and decoding a protocol and that kind of stuff. So it's a little bit overhead, but it should be able to give you something for that overhead. So what's not in scope? Thread safety. You can put on a thread safe queue on it and you can do, that should more or less take care of that. There is some common data structures inside, but they are const, so that should be fine. Continuous processing, that's also out of scope, just insert events to do that. Time handling and states. If you know UML, you can have this and states, which several states are active at the same time. That's also left outside, so just do 2 of them. And yeah, that's more or less out of scope for this. So the basic idea, the classical, use an object or a class to model a state. Some nice benefits, you can use the constructor for the entry state, the destructor for the exit state, very easy. When you start thinking about this, you kind of start wondering, can I use inheritance to model this state hierarchy? And no, you can't, because the lifetimes are different. So it's more like a stack of objects where you construct the states on top of each other, and then you destruct them when you go down and construct them again when you go up. The events, I like the model where the events are an object where you can put in a queue, you can copy them around. It's not a function call that like the state pattern does. It's a design decision. I like it this way. Run to completion semantics. That's the important one, I think. When you start running your function, you want to be sure it ends before you enter some other state and when you call something else. So that's why I included a little queue here to take care of serialization of event objects. And the delivery is going through this event function that every state class needs to have. So how do you use this? I hope my code is readable on this. You have a class, my finite state machine. You call set start state, that activates it. All the entry actions or constructors are fired up till that state, and you're ready to go. Then you just post event until you're done and everything destructs. How does this class look like? It's an ordinary class, nothing special. It inherits from this FSM base. That's part of the framework. You have this myFSM desk or description. That's another class you're using to describe the structure of your state machine. I'll get back to that one. Other than that, there's nothing special in the actual state machine class. You can have some additional data that's accessible from outside or from inside the states. So that's a good place to keep stuff that has the lifetime of the state machine. So now if we go into the state machine itself and look into a state, how does that look like? Class my state. It needs to inherit from statebase. That gives us a couple of functions you can use in your state class. It's also templated on this description class, so you have all that. And you have a dual representation here of states. One is the actual class type. The other one is an enum enumerating all the states. A little bit of a violation of one definition rule, or just the dry rule, I should say, the dry rule. But I need both to be able to calculate on it on runtime and at compile time, so both are needed. The constructor is a little bit of boilerplate. I need to pass arguments down to the base class, and since this framework is actually constructing these objects, so I need to pass the args down. Other than that, you're free to put your entry event code in your constructor. Nothing special in the destructor, just your exit code. And then the main functions are handled in this event function, where your event type is input. That can be a primitive type, like an integer or floating point, or if you want that. And then you do something interesting, and if you want to switch state, you do this transition function. Then you go to the next state. True and false, depending if you want to continue down through to your parent states or to a lower level, sort of. So that description class I talked about, it ties together the event class, my event, the finite state machine name. It should be a state using states equal, or state ID equal state, I missed that one. And then finally a setup states function that describe the structure, how all these states are tied together. And it's just a number of add states function calls, where if you only have the state 1, state 2 here, they are at the root level, level 0. But if you put it a second argument, that's the parent state, and that's how you go up a level. And you can do that recursively up to, there's no set limit for it. So that's the basic use case of it. What does this buy you? What can you actually use this for? Or what does this offer you when you want to write your states? In the state base that you inherit into your states, you have the transitions. You can do it either by type or by this ID number. So you can do it runtime calculated if you want to. You get a reference to your state machine, so you have all the data that you got stored there. And you can reach down to your parent state if you know its type, which you should do since you're the writer of the state machine. So you can access data down there. And that can be useful if you want to have data that has longer lifetime than your current state, but you're a number of small states that cooperates within a larger parent state. And once again, going out to the outside, looking at the state machine, what does that one offer? You can query the current state. You can, once you know the current state, you can actually deduce the type of the state, and you can get a pointer to it that allows you to inspect what's going on inside that current state. Active state in this case, then that's allowed to go down all the way to root if you're on a higher level. So you can any of those objects. And the last part that's written but not in the code on GitHub is set state change callback. So you get a callback each time you do some kind of stage jump in this one. And that can feed another state machine if you do it, if you want to do it like that. So that's how you use it. Some mechanisms that I'm used when writing this one. Placement, new, and delete. So when you construct and destruct state, there's no memory allocation going on here. You set up memory so you have it for the maximum size for each level, and then you do placement, new, and delete, which is just function, constructor and destructor called, more or less. So it should be fairly cheap. Set start state, first time you call it on one state machine, it will set up sort of a data structure that describe how this looks. But that's const declared and then shared by everyone using this function static object mechanism. State classes are not polymorphic. Sean Parent had a nice talk on how to avoid that one, so I tried it out and worked great. Current status, available GitHub. License to be defined, but MIT BSD is probably the one I'm going to go for. Fairly open. Prototype quality, I've used it for my own projects. It works fine. It's still under development, so the interface is sort of settling in. I think the state classes are fairly set by now. What's going to change is more on the state machines, some added functions, and how the description class is handled. And it's inspired by, if you know, Mikael Rosbacke has written a lot about state machines using C functions and static functions. I borrowed ideas from there, but implemented it here. That's all. Thank you for your attention.